Let's thank Vasco again. So now we can start the discussion. So we have 4 experts in the panel. So Nicolas, Archisman, Chris also, yeah, and Vasco. So I guess what we could try to discuss is what kind of new exotic object or what kind of new exotic physics beyond the standard model we can expect with the next generation of gravitational wave detector, and also how we can measure this new object or new effect. So we can start maybe by the question of the what kind of object or new physics. So Chris, you made a list already of a new object, gravastar, boson star, etc. And there was the last bullet was unknown. So do we have some idea of what would be those unknowns? And also, if you have an unknown object, is it possible to find it in the noise if you don't know exactly? Can we find something that we are not looking for?
Yeah. To my knowledge, there's no known object that is very plausible. Yeah. So I don't know of any object in the literature of about which anyone would say, "Oh, yeah, that's the one you need to look for," because again, so at the top of the plausibility list, or near the top of the plausibility list, I would place boson stars, but even there, you need to fine tune. Again, like I mentioned this, of course, but you need to fine tune the properties of your boson model such that you can get star-like objects that are nearly as compact as a black hole, but not so compact that they will collapse to an actual black hole. So even there, fine-tuning is needed. Then, in the absence of a very obvious candidate, what a lot of people are saying, also because of the delta T argument, the time between echoes, we would have to hope for a macroscopic quantum effect. So something that uh, gets rid of the horizon. But then, of course, you have a macroscopic object, and it's not a black hole anymore, but some horizonless object, where the scale of the horizon modification is the Planck scale, but the object itself is yeah, tens of solar masses, and has a radius commensurate to that. So that I think that is what the answer of many people would be for exotic objects. You would have to hope for some macroscopic quantum effect playing itself out.
I'll just add to what Chris just said. So in this case, we need to be open. In order to search for unknowns, we have to be open to options. So it's the how that is going to lead us to the what. So we should, in order to discover the unknown, we have to focus probably on the more unmodeled aspects or unmodeled methods, trying to fold in whatever we know as robust wherever possible. And this is exactly what was done for searches for echoes that Chris was talking about.
Yeah, indeed. All the models that are in the literature, they have certain things in common. Echoes is something that anything horizonless has in common. Yeah, in the case of matter of some form or some field, if that is involved, then tidal deformability is generic. So we know what kinds of things to look for, but we shouldn't be looking for a particular object. Yeah. I think we're saying the same thing.
Comments from the audience? And concerning new physics, so you mentioned this Lovelock theorem and some modification of general relativity that would break one of the legs. Which leg do we think will be the most sensitive to gravitational wave modification?
So as soon as you introduce things other than a metric being involved in gravity, so so there are these models where it's not just a metric that governs gravity, but there's additional vector and or scalar fields. This I didn't talk about at all actually for lack of time, but what you almost immediately get is alternative polarization states. So gravitational waves come in GR come in two polarization states, but in tensor vector or tensor vector scalar theories, you immediately get alternative polarizations, which actually to me suggests that probably tensor vector scalar theories are just generally ruled out.
So you mean that actually we have a proof that there is only two polarization for gravitational waves?
No, you could what we have strong evidence for is that if there are other polarizations, they will be very weak. So that doesn't exclude a tensor vector scalar theory, but it makes it less plausible, I would say. That tensor vector scalar theory is describing the gravity of nature. Yeah.
And concerning, for example, the addition of extra dimension, what will change in the either gravitational wave propagation or the pattern that we expect? Is it going to change a lot if we have a fifth dimension, a compact fifth dimension, or an open fifth dimension?
Yeah, it has to be an open one then almost, so that indeed the idea being that matter is confined to the three spatial dimensions that we're accustomed to, and only gravity can leak into extra spatial dimensions, then you will then the amplitude of a gravitational wave will drop off faster than one upon distance. And you will notice then if you compare EM with GW observations, for instance, EM is stuck to the three spatial dimensions that are special in a sense, whereas only gravity can leak out. Yeah.
So it would be necessary to compare the luminous distance that you extract from the electromagnetic wave from the one you obtain from the gravitational waves signal?
I think so, because if you only have the gravitational wave measurement, then you have a degeneracy between the chirp mass and the distance. Yeah.
Comments or idea from the audience concerning modified gravity? So there was extra dimension, there was other field, there was also.
No one has, maybe I have a comment. I think it also depends on the scale that you want to test. Like I think there is a general consensus from people in modified GR that adding more terms in the Lagrangian, it's probably effectively work to capture possible deviations to GR, and in this sense, probably like ring down tests are going to be more sensitive given the larger curvature that they probe compared to other tests. But as you were correct, I mean, I agree on the fact that tests on the excitation of different polarizations, it's something that is complementary to ring down analysis in this sense, and it's a very strong tool to rule out theories on other regimes.
So in this Lovelock, there is also the possibility to have non-local gravity or derivative above the second derivative. Is this also something that can be tested that would modify the propagation of gravitational waves, maybe not following the D'Alembert equation?
Yeah. So higher derivative gravity is something that would break Lovelock's the assumption of Lovelock's theorem, and therefore, it's worth looking for. Yeah, but we don't. Yeah, we don't look for any specific alternative theory because we can't. We don't have the waveforms, so it's a practical matter. Yeah. Maybe in the future, yeah. I mean, it would be fantastic if each theoretician having a favorite theory would come up with you know, a very accurate in-spiral merger ring down waveform, because if in the model independent tests you start seeing something weird, then the only way of inferring what it is will be hypothesis ranking, which I also didn't talk about for lack of time. But if you have good quality waveforms for a variety of qualitatively different alternative theories, then that would be the first order method to try and find out what it is that's going on. That's different from GR. Oh, yes, also. Yes.
The audience.
How many events do you need to be sure there is a deviation from GR? Let's suppose you see one in one event, but of course you will not believe it if it's just one event. So when we will be sure in case?
No, it's a good question. So, well, on the one hand, it depends on how big the violation is, of course. That's a term. If the violation always somehow is of the same nature for every event, then it is, yeah, then that sets the number of events that you need. But there is conceivably the possibility that only 1 out of 10,000 events will actually show an anomaly. An example would be, and that's actually not something that breaks general relativity, but suppose that boson stars actually exist in that compactness, except that only 1 in 10,000 binary inspiral events contains a boson star. Yeah, then it's not going to be funny then. Yeah.
So we have those gravitational wave detector existing and planned. So it does not cover the whole spectrum. Is there a hole between PTA and Einstein telescope? And is there some project trying to fill this gap, or also maybe at the higher frequency?
Between PTA and LISA, there's I don't think there are any conceived projects that try to fill that gap. Maybe Nicola will confirm. But between LISA and between millihertz and ground-based detectors, there are these. We already heard about the moon-based experiment from somebody. I forget. Antoine. From Antoine, there's also a concept of a DESI-GO. It's a instrument up in space but shorter than LISA that tries to fill in this gap. And very high frequency detectors are also being conceived, but they are in very sketchy stages. I don't know. Maybe Nicola would do.
So high frequency, I really don't know how the situation is there. I know there are some detectors that are, some ideas of some detectors that are being pursued. The main idea is that you use coherent magnetic fields in a cavity resonance. When a gravitational waves high frequency pass by, there is an effect, it's called Gesenstein effects. Basically, you create photons from a gravitational waves and you detect the photons. Both from a theoretical point of view and experimental point of view, we are really far from having something functional, let's say. That's what my personal perspective. Between LIGO, Virgo, whatever, and LISA, there are PCR detectors, which basically are detectors like LISA, but lower arm length. And between LISA and PTA, there is, again, a proposal for a, let's say, beyond LISA mission, where the triangle is basically the whole orbit of the Earth. So you put basically the 3 satellites on the orbit of the Earth, and the triangle is basically including the sun. And this will basically give you LISA, but shifted by 2 or 3 order of magnitude, so in the microhertz frequencies. But this is a proposal for, let's say, 2050, 2060, like this Voyage 2050 program of ESA that is looking at proposal in a 20, 30 years time frame. This is one of the proposals for that.
And do we expect new physics in this frequency band or new object, new?
So in microearth, you will see actually the spiral of massive black hole binary. So with LISA, we see the merger. You will see the spiral, which means that you'll be able to see a lot of them because there will be many more spiraling than the one merging. The main problem is that you also have a lot of more galactic binaries. So you will have actually a strong stochastic background of galactic binaries. You will be able to identify a lot of them, but still you will have a big noise that comes from galactic binaries. In the dead sea Earth, there is a lot of new interesting sources. For example, spiraling neutron stars. You will be able to see them almost follow up to merger. So you will have a basically sky localization few hours in advance of a neutron star. There might be intermediate mass black holes. There is also this idea that you have a double white dwarfs merging. Actually, they're merging in the dead sea Earth, so you might be able to see them if they're quite close. And actually, like Valeria was saying, you will have a lot of information on possible supernova mechanism. So there is a lot of interesting stuff in the dead sea Earth, I think. I believe, I'm not an expert, I believe technically it's more challenging because the technology to arrive at the sea Earth is a bit still in development, let's say.
So there is also the cosmological background, the one from the inflation. Do we expect eventually to see it, I don't know, with LISA, or it will be below the noise level, or what's the status of this?
Well, it depends who you ask.
So the background that would be coming directly from inflation would be by now so redshifted that it's too low frequency even for PTA. But of course, what can happen in particular models of inflation is that at the end of inflation and afterwards even that the inflaton decays into other particles, and so that could give a background that is not so redshifted that we don't see anything. That could be in the band of LISA or conceivably even ground-based, but we don't know. That model then has to be true for that class of models.
You're speaking of the reheating phase?
Yes.
Yeah. Yeah.
This is more a question for Nicola, I think. In the next years, we will probably observe an astrophysical background. Do you expect this measurement to help you to give constraints on H0 or on cosmological?
Excellent question. Actually, there are few papers that came out in the last few months that are looking at how you can constrain cosmological parameters by basically making a population analysis, taking into account both individual binaries and a possible stochastic background. That you can do if you see the stochastic background, of course, and you can detect it with a significant SNR, you can do this kind of analysis. And if I remember correctly, they show that, I mean, depending on your strength of the stochastic background, you might improve cosmological parameters. The analysis that I saw saying that with O5 or 4 or 5, we're not expecting to improve anything because we're not expecting to see stochastic background, or if we see it, we're not expecting to see it at the level you can make population analysis. But for example, for 3G detectors, it will be basically something that we have to do, and nobody has looked into that. It's something that people are looking at actively, how to combine the two.
Okay, but just a curiosity, so I'm not very much deep in the field, but I would be curious to know if there would be some experimental signature that you might predict in the sense that we need to modify gravity to, for example, reconcile or give kind of explanation of dark matter. Is there, I mean, it's a too difficult question or too stupid, I don't know.
Experimental signatures of dark matter? You know, that's the question.
I mean, you are talking also of possible modification of gravity in some sense, no? And is there any specific signature in measurement that you might expect if gravity has to be changed in the direction of justifying also dark matter?
So maybe, for example, TVS or things like that.
Well, what I mean, I think Chris is more an expert than me, but there are some analyses that look at like dark matter spikes in a binary, for example, or the drag, the accretion or drags that say high density dark matter might have on spiral binaries. But I'm not an expert on this. I don't, Chris, if you know more. It's the only thing you can actually look at now, but you need really dense dark matter in order to influence the dynamics of two black holes, for example. So you might be able, for example, if I remember correctly, people look at if you see a binary deep into the center of a galaxy where you have a dark matter spike, then the density might be high enough with, and then with future detectors, LISA, whatever, we might be able to see something. But not, I believe nobody thinks that we can see something with LIGO and Virgo as they are.
The other thing about dark matter, which I'd like to add, is that subsolar mass black holes could also be primordial. And could be a dark matter candidate, and searches are on for subsolar mass black holes, which are observable in the LIGO Virgo band.
Yeah, I just wanted to add that there are models in which you can create super radiance through dark matter, which will be possibly an observable effect with LISA. It's related to the amount of spin of a black hole surrounded by a dark matter cloud, and which can produce radiation. And it can produce radiation at specific frequencies that you will be able basically to observe, and will allow you to test the distribution of matter and the properties of the black hole simultaneously. It's yeah, there is a lot of ongoing work on this field.
Are you referring to the idea of an ultralight boson using superradiance to form a boson cloud, or something other than that? It's that mechanism, yeah. Okay.
Which it can also exist without dark matter, but there are also people that are trying to connect the two things.
Comments from the audience?
One last thing about dark matter, there is another signature that might be on this dark matter, ultralight bosons, fuzzy dark matter, whatever. So in this case, you can see, because basically you have a dark matter potential in the galaxy that is fluctuating with some frequency, you can actually see this effect on an inspiraling waveform if it's strong enough and you have a good sensitivity. But again, it's very, very far in the future, some kind of measure. But there are a lot of ideas to detect dark matter. I believe none of them works with standard lambda CDM called dark matter. So you will need something more to detect dark matter with gravitational waves, let's say.
In your talk, you mentioned to measure or to constrain H0 and also omega m. Do we expect in the future to constrain all the cosmological parameters, the 6 basic cosmological parameters, even without looking to any photons, just with gravity? Would it be possible to have this, a constraint on all the cosmological parameters?
So if you have infinite sources, yes. So the problem with the other, so it's not omega m, it's fine. They drive the background expansion, so you can measure them from the distance ratio relation. I'm talking about lambda CDM. The other 4 parameters depends on the perturbations. So you cannot detect them with gravitational waves unless you have so much sources that you basically can do the same you do with the standard cosmology, so making a clustering analysis and 2-point statistics in the sky. This is the only way you can access the other parameters that I can think of. So you will need very, very, Einstein telescope might be a good start, but even Einstein telescope, we might get 100,000 events per year. If you compare it with the number of galaxies we are seeing today with DAISY or whatever, it's still not a big number. So.
Comment from the audience, everybody is completely kaput.
my question might be a little bit out of the scope of this discussion, but we've talked about exotic physics, so I wanted to come back to exotic particles. And one place that you can expect to find exotic particles may be in neutron stars or something similar to a neutron star. When do you think we're going to be in a position to make excellent constraints on like the mass and the radius of the neutron star that you might be able to constrain whether or not the matter inside is hyperons, kaons, I don't know, something exotic?
So to a person like me, a hyperon is not exotic. It's known to exist, right? The hyperon exists simply, yeah. But so that is a good question. I think we will need percentage level, mass radius measurements to be able to tell the difference, and of course, as function of mass or radius, to make that kind of determination. It will probably help if we can see finally in gravitational waves the merger of neutron stars, for which we need sensitivity at high frequencies, for which in turn we need Einstein telescope and cosmic explorer. That will, yeah. In the exotic category, there has been work on neutron stars as gatherers of dark matter particles, so that neutron stars actually have a dark matter core, and that could have a strong effect on tidal deformability and cause an apparent inconsistency between the equation of state you are inferring and known properties of bulk nuclear matter. There is work in that direction.
Other question for the experts here from the audience?
I don't have a question. I have a comment, which is based on the question that Michaela asked after Nicholas talk about people having tried to use neutron star masses for cosmography, for spectral science. So people haven't used neutron stars, but there's one group that has tried to use NSBH, neutron star black hole mergers. The good thing about neutron star black hole mergers is that you can see them too far away. And they are also, you can see them too farther away. However, the bad thing about neutron star black hole mergers is that the neutron star mass distribution that comes out from there is not only wide, it's also different from 1.4, which you get for for galactic neutron stars. So this particular group, which includes an unnamed Nobel laureate, they tried to select the set of events which would give you a nice H0 value. And they have made an analysis and produced these results without explaining well why they use these particular neutron stars for the analysis.
You mean with the neutron star we detected so far? I mean, the
with the NSBHs that we have detected so far. So we have about 5 or 6. They have selected only 2 that work.
They got a really great.
It's not really great. It works, but they sell it as really great, and this is the way to go.
Fair enough.
Other questions or comments or ideas? No? Okay. Maybe I have a last one. I was wondering whether there was some study looking to new ways to detect gravitational waves, maybe not using light or using other kind of systems. Is there any new ideas in?
Well, I can mention atom interferometry. We mentioned the ideas of the moon. So the idea of the moon is that you put basically seismographer on the moon, and you use the moon as a resonating bar. So you detect the normal modes of the moon that there is gravitational wave passing through. This will basically resonate, and you can see it with seismographer. Other ideas, I don't know. Well, resonant bars is not a new idea, it's an old idea. it has been done. It didn't work. That's that's the main. Yeah, it's true. But high frequency, yeah, I don't know if it works or not. There are some ideas about using clocks, like atomic clocks. If you put them in space, they are basically like pulsars. So you can basically use them, but we are very far away from having the technology to do that. Then I don't know. I don't know any other idea I can think of.
Well, if there is no more ideas in
There is
the audience.
astrometry. It's I got a new one. So like if you have astrometric measurements like Gaia, you can do a similar analysis than PTA. So if you see same stars, different interval, and then you have a gravitational wave passing through, then the actual position of the stars will wobble a bit because of the gravitational wave passing, and you can use this to the gravitational waves. The paper that I know that explore these techniques show that with Gaia we are far away from the sensitivity you need to detect gravitational waves, of course. But in a future, if you have a Gaia times 100 times better, I don't know, you will be able to do it.
The frequency band is related to the distance to the.
It's going to be like PTA. Continuous way to detect the gravitational waves. Ah, yeah, that was another idea, but it doesn't work. So this is actually, no, this is actually a nice idea that we thought about this like 10 years ago with Lisa. We see a lot of, I think with Valeria also, we had a workshop and say, why don't we use galactic binaries like pulsars? But the problem is that the reason to use pulsar is that the timing, the actual timing, the uncertainty on the timing is 10 to the minus 15. It's crazy. I mean, it's like the pulsars are like atomic clocks in space. The accuracy you have on the frequency of galactic binaries with Lisa is like, even, I mean, it might be good, it's like 10 to the 6, 10 to the minus 6 in the best cases, but you're 10 orders away from, from 10 to the minus 15. So it didn't work. Although a couple of years ago, I saw a paper that they put out the idea and say, you can do this, and then show the plot 10 order of magnitude before.
Okay, I think we should stop here, and thanks again the expert from the panel.